So precipitation reactions, acid-base neutralization reactions, and the gas evolution reactions all involved taking the reactants apart into their ions and swapping partners and putting them back together. In an oxidation-reduction reaction, it happens a little bit differently. So here what we have is electrons being transferred from one reactant to another. So they're called oxidation-reduction reactions or redox reactions. Many of these types of reactions involve something reacting with oxygen. So some examples here, rust. So iron reacts with oxygen to make iron oxide. Here, the iron in the reactant is the element. It doesn't have a charge. It's not an ion. The iron in the product is an ion, part of this ionic compound. Metals become ions by losing electrons. And if the iron loses the electrons have to go somewhere. There's no shelter for electrons. They have to go directly to somebody else. And so here, the oxygen is accepting the electrons. So we have a transfer of electrons. This combustion reaction of, I believe that's octane reacting with oxygen, forming CO2 and water. This is also a redox reaction. Hydrogen gas and oxygen gas reacting to form water, also a redox reaction. The transfer of electrons is not obvious in these two reactions, but it is more obvious in the iron. So when we see something reacting with oxygen, a lot of times that's a redox reaction. Let's look at the combustion reaction. So hydrogen reacting with oxygen is also combustion, forming H2O. So in this balloon, we have a mixture of hydrogen gas and oxygen gas. And that'll just sit there very nice, red balloon. But if you put a little spark here, it will do this. Kaboom! And I remember as an undergrad in one of our science shows, chemistry shows, the balloon was maybe a little too big. And they had it like halfway up to the ceiling in this large auditorium. And so, candle on a stick, and it lifted all the ceiling tiles. They all went whoop, and we're like, "Ooh, that was a little too fun." But that was before the days of people shooting up campuses and stuff. And so when people heard loud booms like that, they're like, "Oh, the chemists are messing around again." Now, when we make noises like that, we sometimes get into trouble. It's just a combination of hydrogen with oxygen. It's a very vigorous reaction. It releases a lot of energy. This is a redox reaction that does not involve combustion. And we've looked at this before. Here we're reacting two elements, a metal and a nonmetal, sodium and chlorine. Chlorine is this yellowish gas, and sodium is a soft metal. And when these react, they form sodium chloride. You can see the little crystals in there. This is also a rather vigorous reaction. So what's happening here is we're starting out with sodium atoms. These don't have a charge. And we have molecules of chlorine, two atoms hanging out together because they don't like to be alone. And the sodium, each sodium atom will transfer one electron to a chlorine atom. Because over here in this sodium chloride, we have ions, right? We have sodium ions and we have chloride ions. And the sodium chloride is formed because of the attraction between the oppositely charged ions. Sodium atoms became sodium ions by losing electrons. Chlorine atoms became chlorine ions by gaining electrons. There's a transfer of electrons. It's a redox reaction. Any questions?
Think about neutral atoms, no charge, until
right.
They're combined with some sort of compound.
Yeah. So a common problem is that I got the message through to you that we predict charges from the periodic table maybe a little too well. And so then I was finally looking at experiment 3A, where you had to write the equation for the reaction between zinc and iodine. And so it was two elements, but some people got a little carried away and they said, well, it was zinc reacting with iodide. No, it was zinc, the element, reacting with iodine, the element. So an element doesn't have a charge. When it becomes an ion, many of them have predictable charges, but an element by itself doesn't have a charge. So Zn2 plus and Zn are different. They're very different. I minus and I2, very different. So let's look at these. Here we're going to look at metals reacting with nonmetals. Here we have a metal reacting with oxygen, so we could say, well, that might be a combustion reaction, and it does fit that category. The element sodium reacting with oxygen to form an ionic compound. And we also just looked at sodium reacting with chlorine. Again, a metal and a nonmetal reacting to form an ionic compound. There were no ions in our reactants, and we have ions in the products. Ions are formed by gaining or losing electrons. So a metal reacting with a nonmetal is going to be a redox reaction. We can look at this in a non-standard way, and we see that we've got sodium atoms and oxygen atoms hanging out together in a molecule, and in the compound we have two sodium ions and one oxide ion. And when you look at this mess, you kind of get an idea of why we don't include charges in our formulas for compounds, right? It gets really messy, and it's unnecessary. So this is what we have in this compound. Here, the sodium and the chlorine reacting. Now we have sodium ions and chloride ions. There were not ions before. Electrons were transferred. So to become an ion, an atom must either gain or lose electrons. If one atom loses electrons, another atom must accept them. If an atom gains electrons, somebody else has to lose them. There is no electron bank where you can go and make withdrawals of electrons. There's no electron homeless shelter where you can deposit unwanted electrons, and you can't leave them by the side of the road. You have to pass them off to someone. So the electrons are always transferred. When an atom loses electrons, that's called oxidation, and when an atom gains electrons, that's called reduction. So a good way to remember this is with the sentence, sort of a sentence: oxidation is loss of electrons, reduction is gain of electrons, abbreviation oil rig. Oxidation is loss, reduction is gain of electrons. So here we see the sodium becoming a sodium ion. It does that by losing an electron. Oil, oxidation is loss of electrons. The chlorine gains electrons to become a negative ion. That's a reduction. So it's relatively easy to see how that transfer of electrons occurs between a metal and a nonmetal, because the transfer actually occurs completely and then we get ions. But we can also get an incomplete transfer, just sort of a shifting of electrons. And that happens when we have two nonmetals reacting. So here we're going to look at the reaction between hydrogen gas and chlorine gas. So we could illustrate hydrogen like this. So here's the two hydrogen atoms, and this red area in the center is where the two shared electrons are that form the bond that hold those two together. Because these two atoms are identical, they're going to share the electrons evenly, fairly, equally. Here we have a chlorine molecule, and it's sharing its electrons as well. I mean, you could think of this in terms of taking the blankets. each person in the bed is equally strong and aggressive in terms of the blanket, and so it kind of comes to a truce, right? And so the blanket kind of stays shared evenly. When these two molecules react, though, we get hydrogen forming a bond with chlorine. And chlorine is more of a blanket hog. Chlorine is more of an electron hog. So when we form this new compound between hydrogen and chlorine, now the electron distribution shifts and the chlorine gets the electrons more. It doesn't become an ion, but it's got more of the ion of the electron, So it's not like the chlorine has totally taken the blanket and gone off and slept in another bed. Still sharing a bed, still sharing the blanket, but hydrogen's only getting a little bit of the blanket and chlorine's getting more. Whereas before, they were shared equally. So this is a shift of electron density. And so this also qualifies as an oxidation-reduction reaction. So the chlorine increases its electron density. So it gains electrons, not an entire electron, but part of an electron, and so that's a reduction. The hydrogen loses electron density, and so that's an oxidation. So when we're looking at reactions between nonmetals, it's a bit tricky to identify, is this a redox reaction or not? If we see a reaction that's combustion, something reacting with oxygen, that's also a redox reaction. If we see a metal and a nonmetal reacting, they form ions, that's a redox reaction. But when we have two nonmetals, it's a little trickier. And so we made up something called oxidation states, they're also called oxidation numbers, to help us figure out, are electrons being shifted, and if so, in what direction? So oxidation states are not ionic charges, they're imaginary charges, okay? Ion charges are real, ion charges can be measured. Oxidation states are made up. So they're sort of pretend ionic charges. And what makes it kind of confusing is that oftentimes if something has an ionic charge, that charge is the same as the oxidation state. So there's a set of rules for assigning oxidation states. And, when, like many things, when you spell all the rules out, it makes it look more complicated than it really is. So basically, if something has a charge, if a single ion has a charge, its oxidation state is the same as its charge. If you have an atom, no charge, its oxidation state is 0. So that's kind of what the rules say. Free elements have an oxidation state of 0. So copper or chlorine, if you have an element by itself, oxidation state is 0. Because if you looked at this Cu, what's the charge on that? Well, we can look at the periodic table and maybe get an idea of what it might have, but as it's written here, it has no charge. And Cl2, no charge. So those oxidation states are 0. Monatomic ions, a single atom that becomes an ion like calcium or chloride, the oxidation state is the same as its charge. So calcium has a +2 oxidation state, chlorine has a -1 oxidation state. And then oxidation states behave like ion charges in that when you sum them all up, in a neutral compound, they have to add up to 0. And if you're looking at a polyatomic ion, the sum of the charges has to equal the overall charge on the ion. So if we have this compound H2O, we know that the oxidation states of hydrogen and oxygen must add up to 0, just like the charge on H2O is 0. Nitrate ion has a -1 charge. The oxidation states of the nitrogen and the 3 oxygens add up to -1. Metals always have positive oxidation states. They're the same as their ion charges. nonmetals are really the reason that we need the oxidation states, and so they have a list of priorities here. So after you assign oxidation states to any of the ions, like sodium or something, and then you're down to just nonmetals, and you're trying to pick, well, who gets what. So this is how I think about it. The nonmetals would like to have an oxidation state the same as the charge they have as an ion, right? So fluorine forms a fluoride ion with a -1 charge. That is the oxidation state that it would like to have, okay? Oxygen forms an oxide ion with a 2- charge. If oxygen had its opportunity, it would have a -2 oxidation state. Now, they don't always get what they want, but that's what they want, okay? So then this list tells us who gets to pick first. So we go through the nonmetals we're trying to assign oxidation states to, and fluorine gets first choice. So fluorine's always going to choose -1. Next up is hydrogen. Hydrogen gets to choose. Hydrogen's going to choose +1 because that's the ion it usually makes. Then is oxygen. Oxygen will always choose -2. Again, the charge that its ion would have. And then it's anything in group 7, anything in group 6, anything in group 5. So we need to be able to remember this list. Anybody like Vietnamese noodles? What are they called? Pho. Right? Pho. Well, what if I just kind of knock the end of that off, the end of the P? You could still pronounce that pho, right? This is like even more phonetic. All right, so FHO, and then 765. So pho 765. There's actually a restaurant, pho 76. You just need to add a 5 on it, and they'll have the non-metal oxidation states down. Pho 765. So you think you can remember that? And that's fluorine, hydrogen, oxygen, 765. So we'll do some examples, and I'll repeat that over and over again. It's possible to have fractional oxidation states. We don't run into it much in Chem 1A, but it's possible. And just so you know what the convention is, the sign is written before the number for oxidation states. It's written after the number for ionic charges. I won't try to trick you on that, but just so that you don't wonder, why do you keep moving the sign back and forth? Well, one's an oxidation state and one's an actual ionic charge. Okay, so let's practice. We're going to assign oxidation states, and each atom gets its own oxidation state. So we don't look at them lumped together, we look at each individual atom. So we'll start off kind of slow. Here's chromium. Is there any charge on this? No, it's 0. This is an element. So what is the oxidation state of that atom? 0. Here's chromium 3+ ion. So what's the oxidation state for this? 3. If there's a charge on a single atom, a single ion, the charge and the oxidation state are the same thing. Okay? Here we've got carbon tetrachloride. There's 1 carbon and 4 chlorines here. They're all nonmetals, and so we have to dig out Pho 765. So Pho 765. Is there a fluorine there? No. A hydrogen? Nope. Oxygen? Nope. Anything in group 7? Chlorine. So chlorine gets to pick. What's chlorine going to pick? -1. So the chlorine is going to be -1. So the chlorine is going to have a -1 oxidation state. And then we have to figure out what the carbon oxidation state is. This is a neutral molecule, so all the oxidation states have to add up to 0. I have 4 chlorines. They're each -1. I have 1 carbon. Must be +4. So the math involved here is just like the math with ions. This is just like figuring out if this was some transition metal, what would its ionic charge be? It's the same idea, but these are made-up charges because nonmetals don't have charges together. Any questions? And this list just tells us who gets first pick. This is for the nonmetals. This is after you get through everything else. Yeah. So that list of rules, we go through them in order. If you've got an element by itself, it's 0. If you have a monatomic ion, the charge is the same as the oxidation state. All the oxidation states have to add up to the overall charge of the thing, right? And then when we get down to the nonmetals, this is our way of choosing. And it's based on some bigger principles, but this is easier than going through all those bigger principles. So let's look at this one, SRBr2. Well, there's a metal and a nonmetal, right? Do these things actually have ionic charges? Yes, they do. So the ions here, we have strontium ion and we have bromide ion, 2 of them actually, right? Those are actual ions. So then the oxidation states are easy because the oxidation states are the same as the charges. So for strontium, the oxidation state is +2. And for bromine, the oxidation state is -1. Each bromine is -1. Any questions? SO3. Are there any ions in that? No, because it's just nonmetals, right? So then, Fe765. Any fluorines? Nope. Hydrogen? Nope. Oxygen? Yes. Oxygen gets to pick. What does oxygen pick? -2. Because that's the charge it would have if it got to be an ion. So the oxygen's going to be -2. There were 3 oxygens. So the sulfur has to make up the difference so that overall all the oxidation states add up to 0. +6. So if this is mom and she's got three kids with her and they're each buying a popsicle that's $2, how much money is mom out? $6?
Do you want us to just leave it as like oxygen -2, or do you want us to actually be like, oh, it would be -6?
That's a good question. We want to look at each atom by itself. So here, each of the oxygens is -2. So we don't want to say together the oxygen's -6. That doesn't really tell us anything useful. The only thing that's useful for is helping us to predict what this charge oxidation state is. But we look at each individual atom. Yeah.
So that one, kind of not a shortcut, but how this we corrected it in my head. I just usually switch the numbers and then look at their charges on the periodic table and add that. Right?
Yes. It's very similar to what we would have if we had some metal, M, that had 3 oxygens and it was an ionic compound. And we'd say, oh, well, each of the oxygens has a 2- charge because that's the ion that they make. And then we know from the ratios that the metal must have a +6 charge, because we have 3 of these guys.
Even though we know sulfur is a charge.
We know that sulfur, if it was an ion, would have a negative charge, but it's not an ion here. It's an atom still. So the sulfur is sharing electrons with oxygen, but it's not sharing them equally. The oxygen hasn't taken electrons, but it's hogging them. And so sulfur has lost some of its electron density blanket. And so we use the oxidation states to see who's winning in the blanket wars, if that helps. Yeah?
For monatomic ions,
Mhm.
so like calcium, in the previous
Mhm.
example, there's kind of 2+, so like, say, we were given potassium by itself, there's nothing, no charge.
Mm-hmm.
Would we assume that there's a charge?
No.
Plus, no?
So if I'm given K and asked to assign the oxidation state, that is not part of a compound.
It has to be written.
It would have to be written.
Okay.
If I meant potassium ion, I would write K+.
Right.
Yeah.
So how monatomic ion?
Well, this is an ion that is formed from only one atom. So chloride is a monatomic ion. It's a chlorine atom that gained one electron, as opposed to a polyatomic ion, where you have a group of atoms together that act as a unit with a charge. Does that make sense? So we've got atoms and ions. And ions are atoms with charges. I know, so many details. So let's look at this polyatomic ion. Overall, it has a -1 charge. That tells me all the oxidation states have to add up to -1. But nitrogen and oxygen are both nonmetals. So if we were going to look at what they want to be, they both want to be negative. Nitrogen would like to be -3, and the oxygens would like to be -2. But if they all had their own way, we'd have a -9 charge on this, and we don't. So the oxidation states tell us how to assign these imaginary charges. So again, F765. Fluorine, nope. Hydrogen, nope. Oxygen, yes. Oxygen gets to pick. Oxygen always picks -2. And so here we have 3 of those -2, and we have one of the nitrogen, I'll call it X. And that has to add up to -1. So people think about math like that in very, very different ways, but we should be able to come up with the answer +5. The nitrogen has a +5 oxidation state. It doesn't have a +5 charge because nonmetals don't have positive charges. But in this sharing of electrons between these nonmetals, oxygen is pulling that electron blanket away, and the nitrogen is short. It's out in the cold. Any questions? Yeah. Pardon me? So when does it have to equal at -1? Well, it has to, the sum of the charges of all the atoms in the thing, whether it's an atom or, a molecule or an ion, have to add up to the charge on it. So this had a charge overall of -1, so they all add up to -1. SO3 is a molecule without a charge. Its charge is 0. So then all the oxidation states add up to 0. Okay? Yeah, when you see that, it's like, oh, well, that's not so hard. Yeah.
So for how you got positives, how'd you get positives?
How did I get +6 for E?
Yeah, this one.
So I'm going to erase some of these scribblings over here. So I can do some different scribblings. So SO3, we could imagine it looking like this. We've got sulfur, and it's sharing electrons with 3 different oxygens. And so there's no ionic charges. But if we were going to make up charges, which is what oxidation states are, this oxygen would be -2, and this would be -2, and this would be -2. We know from looking at this formula that has no written charge that there is a charge of 0. It's neutral. There's no positive, no negative. So if this one's an imaginary -2, imaginary -2, imaginary -2, what does this one have to be so that they all add up to 0? I almost said it. It has to be +6. Okay? They are very like ionic charges. And that's nice because we've already learned how to do ion charges and to figure out, like on this one, if we didn't remember what the charge on strontium is, we could figure it out because we know the charge on bromide. It's the same process to figure out what these oxidation states are. What's tricky about it is that because it's similar with ion charges, we get them mixed up sometimes. Because we say, well, how could sulfur be +6? It's a nonmetal. You said nonmetals always form negative ions. They do. This isn't a real ion. It's imaginary. We're pretending. Okay? Does that help? Anybody else have any questions? Yeah.
Isn't nitrogen become -3 from the front thing?
That's a good question. Why didn't nitrogen?
It's in group 5.
Right. So nitrogen's in group 5. So this is an order. They're in line. And so the guy at the top gets to choose first. Yeah. So oxygen chose first, and then the last guy has to make up the difference. So yeah, he just gets whatever he has to have.
So if it's part of the 765, the other molecular element is based off the first one.
Yeah, so we go through FUS 765. If there's only 2 elements, then the first one we find gets its charge. The other element has to be whatever it is to make up the total. You could have something where you have 3 or 4 elements. And then you go through, and the first one you come to gets to pick first, and the second picks, and then the third picks. And the last guy, however many there are, makes up the difference.
So if there's more than 2, you still just keep going?
You just go through. You start at the top and you go through. Mm-hmm.
I'm sorry, what happens if it's not on this? Is it we do the...
So if it's not on this list, it's going to be a metal. And the metal is going to have an actual ionic charge. And that will be the same as its oxidation state. Yeah. Good questions. Because this is how you put the pieces together and see what the heck is she talking about. Yeah, if we saw calcium in a compound, like this, well, that's a bad C. It's a bad Cl. If we saw this, that's an ionic compound, right? And so we have learned that this is a calcium ion and 2 chloride ions, and we know what the charges are. This is a calcium 2+, because it's in group 2. And chloride here is an actual ion. It has a -1 charge. So the oxidation states here are the same as the charges. So if it has a charge, the oxidation state is the charge. It's the same. It's just when we have something like H2O, there's no charges there. We don't have a metal, non-metal. It's actually not the best example. Let's do CO2. Who's positive? Well, there aren't any positive ions there because there aren't any metals. And so then we have to decide by going through FUS 765. Question? No?
So once it's a metal and a non-metal, you can do the ionic charges, but if it's not, then you do the plus
So if you have metals or nonmetal ions, you use the ion charges. And so Fu765 is for when we can't figure it out based on ion charges. Yeah. So let's look at this. Again, oxidation is oil. Oxidation is loss of electrons. Reduction is gain of electrons. Those terms actually came from observations made before we knew what electrons were. And oxidation means that something gets oxygen. So when natural gas burns, the carbon reacts with oxygen and becomes CO2. The carbon gets oxidized. So it's an oxidation. Oxidation states help us to understand this. Oxidation is an increase in oxidation state. To increase your oxidation states, becoming more positive, that would be the same as a loss of electrons. Reduction is a decrease or a reduction in the oxidation state. The oxidation state is going down, is going more negative. How does it become more negative? By gaining electrons or gaining imaginary electrons. So when we have a reaction between two nonmetals, here carbon and sulfur, and they're going to form this compound, you wouldn't be able to predict that, but we just have to tell you this is what it makes, CS2. Well, here the oxidation states for carbon, the element is 0. For sulfur, the element is 0. When we look at CS2, we're going to use Fu765 to predict the oxidation states. Fluorine, no. Hydrogen, no. Oxygen, no. Group 5, no. Group 6. Sulfur is in group 6. So sulfur gets to choose what it wants. What ion does sulfur make? -2. So it's going to choose -2. It's not an ion, but it's pretending. So this sulfur is -2, and the other sulfur is -2. And then there's only one element left, and so it has to make up the difference. This is a neutral molecule. All the oxidation states have to add up to 0, and so the carbon ends up being +4. So now we can look and see, is this an oxidation-reduction reaction? Did something get oxidized? Did something get reduced? The carbon increased its oxidation state. It went from 0 to +4. It went up. That's an oxidation. Sulfur reduced its oxidation state. It went from 0 to -2. It went down. That's a reduction. So oxidation is oxidation state going up. Reduction is oxidation state going down. There wasn't an actual transfer of electrons, but there was a partial transfer of electrons, and so this is a redox reaction. Yes?
So you use the
Mm-hmm.
thing to determine that S is going to get what it wants, so it's going to be
-2.
-2, and then from there you just have to make it equal to.
Right. So I'm going to figure out the oxidation state on the carbon the same way I would on a transition metal, where I'm looking at how many ions do I have and what are the charges. Yeah, it comes last. Any other questions? Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So here we have to look at each element separately. So we're going to start by assigning oxidation states. So for this tin, what's its oxidation state? 0. How did you know that? Because there's no charge on it. Right? It's SN, it's an element, no charge, 0. We're going to completely ignore the coefficients here. That's just for balancing the equation. I'm just looking at this formula. HNO3. Well, those are all nonmetals. So I'm going to use Fu765. There's no fluorine, but there's hydrogen. Hydrogen gets first choice. What does hydrogen pick? +1. So hydrogen, and next in the list is oxygen. I've got oxygen, so what's oxygen going to pick? -2. There's 3 of them. They are each -2. You could write out 3 -2s if that helps. So then nitrogen has to pick up the slack, be whatever is needed so that these add up to 0. Make that a little clearer. That's a +1. So it's got to be a +5. I have 1 hydrogen with a +1. I have 1 nitrogen with a +5. That's a total of +6. And then I have 3 oxygens that are each -2. And so all of these numbers add up to 0. So let's look at this one. SNO2. Is this an ionic compound? Yeah, it's a metal and a nonmetal. So we're just going to assign oxidation states that are equal to the ion charges. What's the charge on the oxide ion? -2. There's 2 of them, and they're each -2, right? The actual ion charge is -2, and the oxidation state is the same. What's the charge on that tin ion? +4. So its oxidation state is +4. If you have charges, use them. Those are the oxidation states. Yeah. For these, because they're neutral molecules, it adds up to 0. When we have a polyatomic ion like sulfate, SO4 2-, then they all have to add up to -2. So here we've got NO2. Is this an ionic compound? No. There's no metal, right? So there's no actual ion charges. So we're going to use Fe765. So who comes up first, oxygen or nitrogen? Oxygen. What does oxygen want to be? -2. Oxygen gets what it wants a lot. So then what does this nitrogen have to be? +4. So that this +4 and 2 of the -2s add up to 0, which is the charge on this molecule. Yeah. The coefficients aren't going to come into play here at all. No. We're just looking at how does the oxidation state of this particular atom change. So tin is going from 0 to +4. That's a change. The numbers in front are just to balance the equation. Okay, what about water? The overall charge is 0. But it's a molecular compound. So Fe765. Fluorine? Nope. Hydrogen? Yeah. What does hydrogen want to be? +1. There's 2 of the hydrogens, H2. They're each +1. So what's the oxygen? -2. Well, that's convenient. Oxygen likes to be -2. Oxygen and hydrogen are both pretty happy in water because they have their preferred oxidation states. And so that helps me predict that water is a stable molecule. You got something where it is a very unhappy oxidation state, it's probably going to react in a way that'll give it a better oxidation state. So any questions about assigning the oxidation states? Yeah. Mm-hmm. Yeah, so if we had nitrate, oxygen comes first in the list, so each oxygen gets to be -2.
So would a nitrogen be 5?
Yes, the nitrogen would be 5. So that nitrogen would be +5, so that when we add all of these up, we get the charge. If it's a neutral molecule, they add up to 0, which is the charge. If it's a polyatomic ion, they add up to the charge. Okay? So we figured out the oxidation states. We're supposed to identify the element that's oxidized and the element that's reduced. So oxidation is an increase in oxidation state. Reduction is a reduction in oxidation state. I mean, that's not too hard to remember, is it? Reduction is reduction, going down. Oxidation is going up. So I'm just going to start with the first element and see what happens. So here's tin. It's at the 0 on this side, and I find tin over here, and it's +4. Is that going up or down? It's going up. So it went from 0 to +4. That's oxidation. So the tin is being oxidized. And in this case, because it's forming an ion, it is literally losing electrons. So then let's look at the rest of these. Here's hydrogen. Hydrogen's +1 here, and we find hydrogen over here, and it's +1. It didn't change. Just ignore it. Here's nitrogen. Nitrogen is +5, and over here, nitrogen's +4. So that's a change. +5 to +4. That's going down, right? It's being reduced. Reduction. The oxidation state is being reduced. And then let's check out the rest of these. Here we have oxygen. It's -2. Over here, there's oxygens all over the place. Oxygen's -2, oxygen's -2, oxygen's -2. The oxygen didn't change. So if we have oxidation, we have to have reduction. If we have reduction, we have to have oxidation. Yeah. That's a good question. Would there only be one thing that's being oxidized and one thing that's being reduced? There could be more. You could have two things being oxidized and one thing being reduced. You can actually also, this is really crazy, you could have the same element being oxidized and reduced. Obviously not the same atom, but it's going into one compound oxidized and into another compound reduced. We shouldn't see that in any of our problems, but it's possible.
Oxygen, they only have maybe 2 out of all of them. What if one of them wasn't like that? So would we choose that oxygen?
Yeah, if one of the oxygens was different, maybe this one was different, and these were all the same, we'd say, well, those are all the same, but we'd still look at this going to something different and say, yeah, that's oxidation or reduction.
If they were all, would it ever be if they were all oxygen?
That could happen, yeah.
So which one would we look at then? If we were,
Well, you'd have to look at all of them. Yeah.
Is it kind of like balancing an equation almost?
It's definitely like balancing an equation.
It's just adding the numbers together of oxygen.
This is a way of keeping track of who's got the electrons. And we're going to talk a little bit more about how you balance these things, where we'll find out that these coefficients are important. And sometimes when you have a redox reaction, in order to balance it, you have to actually look at how the electrons are moving around. You can't just balance it by inspection and have it be correct. Because not shown is some electron transfer going on. And if somebody's losing 2 electrons, there has to be somebody else that's gaining 2 electrons, or 2 guys that are gaining 1 electron or something. Because it all has to even out. Any questions? Wait.
On the last one, didn't O add up to, on the first side, -6, and on the second side, it added up to 8, right?
Well, so the oxygens here may add up to -6, but each of them is -2. And over here, each of the oxygens is -2. So they're moving around, they're becoming parts of different atoms, molecules, or ions, but they're keeping their same oxidation state. we'll come back to that one. Anybody else? So oxidation and reduction have to occur simultaneously. If an atom loses electrons, another atom must take them.
You can't just have one.
You can't just have an oxidation. It's a little bit like buying and selling stuff. I can't buy a sandwich if nobody's selling sandwiches, right? And I can't sell an apple if there's no one to buy it. I can offer it, but if no one buys it, I haven't sold it. So there has to be a giver and a taker. Okay, agents. I wish I didn't have to talk about this, but I do. So we have a tenuous grasp on oxidation and reduction. So then there are also things called reducing agents and oxidizing agents. I know. So let's talk about movies. Let's go to Hollywood, down south. So in Hollywood, you have movie stars and you have their agents, right? Who stars in the movie? The movie star. Does the agent actually do anything in the movie? No. What does the agent do? It finds the jobs for the movie star. The agent causes the movie star to star in the movie. Okay? So here, a reducing agent gets somebody else. Oh, come on. So silly. Here we go. The reducing agent acts for somebody else. It gets someone else reduced. The oxidizing agent causes something else to be oxidized. So if the reducing agent causes something to be reduced, it does so by being oxidized. And the oxidizing agent oxidizes something else by getting reduced itself. So it's opposite. But if you think it's the agent is causing something else to be reduced. So in this for practice, we're going to determine, is the reaction a redox reaction? And here they want us to identify not what's being oxidized and what's being reduced, but what's the oxidizing agent and what's the reducing agent. So there's a couple of different ways we can identify, is it a redox reaction? Is it a reaction between a metal and a non-metal element to form an ionic compound? Yes, it's a redox reaction. Because here I had lithium atoms, here I have lithium ions. Chlorine atoms, chlorine ions. Actual electron transfers taking place. This is a redox reaction. So that's a redox reaction. Or I could assign oxidation states to everything and look and see, is something changing? That would tell me also. The second one, here I have, this is a net ionic equation. So there's a tin 2 ion here. There must be a negative ion somewhere, but apparently it doesn't matter what it is, and so it's not shown. So here I have aluminum atom becoming aluminum ion, and I have a tin ion becoming a tin atom. Think that's redox? Transfer electrons? Definitely. I see metals actually changing what their charge is. So this is a redox. How about this one? Oh, what kind of a reaction is that we studied earlier? It's a double displacement reaction, although I haven't used that term. We look at swapping the partners, right? The lead and the lithium swap partners, and it's a precipitation reaction because of solid forms. If we look at all the oxidation states here, this lead was a 2+ ion, and over here it's still a 2+ ion. The lithium was a +1 ion, it's a +1 ion. The nitrate overall is -1. It was a -1 over here. The chloride is -1, and here the chlorides are -1. None of the ion charges changed. They remained the same. They just switched who they were hanging out with. So there was no oxidation or reduction. Not a redox reaction. That's what we would call that. That's called not a redox reaction. It's a precipitation reaction. How about that last one? Without doing oxidation states, we've got two nonmetals reacting. One of them's oxygen. That makes it a combustion reaction. Combustion reactions are always redox reactions. Reaction with oxygen. Okay, so 1, 2, and 4 are the redox reactions. Now we have to identify the oxidizing agent and the reducing agent. So let's just look at what the oxidation states are and what's going on here. So the oxidation state for lithium. Zero. And for chlorine? 0. They're elements by themselves. Here we have an ionic compound, lithium chloride. Because it's an ionic compound, we can just look at the ion charges. What's the charge on the lithium? +1. And on the chlorine? -1. So the lithium went from 0 to +1. The chlorine went from 0 to -1. So the chlorine was reduced and the lithium was oxidized. Chlorine was reduced, lithium was oxidized. Are we okay with that? I say that because chlorine went from an oxidation state of 0 to -1. That's a reduction in oxidation state. Lithium went from 0 to +1. That's an elevation, an increase in oxidation state. It's oxidized. I think it's best in a question like this to first identify what's oxidized, what's reduced, and then look at the agents. The agents are opposite. So chlorine was reduced. Chlorine caused the other thing to be oxidized. Chlorine is the oxidizing agent. Because the agent doesn't get oxidized, the agent causes something else to be oxidized. And then lithium was oxidized, but by doing that, it caused the chlorine to be reduced. So this is the reducing agent. Any questions? This is one of the most confusing things. Let's look at number 2. Oxidation state on aluminum, Al, 0. On SN2+, +2. On Al3+, +3. And on SN, 0. So we've got aluminum and we've got tin. Aluminum is going from 0 to +3. Is that oxidation or reduction? That's oxidation. So the aluminum is being oxidized. The tin is going from +2 to 0. It's being reduced. Aluminum is being oxidized. What kind of an agent is it? It's a reducing agent. And so the tin is the oxidizing agent. Clear as mud, right? Let's look at that last one. What's the oxidation state of carbon here? 0. And oxygen? 0. Good. One way you could think about this is like, well, here I have this thing is carbon, and overall the charge is 0, right? Because there's no charge written. So that means that the sum of everything in there has to add up to 0, but there's only one thing. It's got to be 0. Here, the O2. This is a neutral molecule. The charge overall is 0. So I have 2 oxygen atoms in here, but their oxidation states have to add up to 0. Now, could you have one that's +1 and one that's -1? In theory, but there's going to be a fight about that, isn't there? Because they're not going to agree. They both want to be -2, and so they're going to both go with being 0, because nobody wants to be +2, if that helps you remember that elements are 0. CO2, Fa765. Fluorine? No. Hydrogen? No. Oxygen? Oxygen's -2. There are 2 of them. They are each -2. What's the carbon? +4. So the carbon going from 0 to +4 is oxidized. And the oxygen is reduced. I cannot think of an example where oxygen gets oxidized. It doesn't happen. So if this is oxidized, that means it's the reducing agent. And the oxygen being reduced is the oxidizing agent. This is one of those things that unless you use this a lot, and I use this every semester, but that doesn't qualify as a lot. Unless you use it a lot, it's best to just think it through. This is going from 0 to +4, that's going up, that's oxidation, so it's the reducing agent. Notice that oxygen is the oxidizing agent. Oxygen is the original oxidizing agent. That's what it got named for. Any questions? Activity series. So here we have a picture of a strip of magnesium in a solution of copper ions. And we saw solutions like that before, right? A pretty blue color. If we let this sit, after a few minutes, it's going to look like this. What? And if we let it sit longer, notice that the blue color is fading? The blue color would be gone and it would be colorless. What's happening here is that the magnesium metal in this strip and the copper ions in the solutions are trading places. The magnesium is losing electrons to become a magnesium ion. The copper ions are gaining electrons to become copper atoms. Copper solid is not soluble in water. It's a solid, and so it's going to become a solid where it got its electrons, which is on the magnesium. And so this crusty looking black stuff is actually copper. This doesn't really look like copper. So magnesium has a greater tendency to lose electrons than copper does. So this happens. If we try to do the reverse thing, because, well, if you can go forward, why not go backwards? And we put a strip of copper in a solution of magnesium, we can wait forever. It's never going to go back. It's never going to go the other way, where we get magnesium depositing on the copper and the solution turning blue because there's copper ions forming. Copper doesn't lose electrons to magnesium. Magnesium loses electrons to copper. So we have what's known as an activity series, and it's a little bit like that Fuzz 765 thing. It's a list of who's stronger, who gets what they want. So the activity series lists metal in the order of decreasing tendency to lose electrons. So at the top is the one most likely to lose electrons, and at the bottom is the one least likely. So we write these as if they were oxidations. Oxidation is loss of electrons, so we're looking at the losing electrons. And that's called a half reaction because it's only half of what's happening. If we turn one around, it's a reduction half reaction, and you put two of them together to get one reaction, and that didn't make any sense at all. Okay, so here's our activity series. The good news is you do not have to memorize this list. So up at the top is lithium, and lithium is the most likely to lose electrons, and down here in this list, gold is the least likely to lose electrons. So what we have here is a reaction showing a lithium atom losing one electron to form a lithium ion. It lost electrons. It went from a 0 to a +1 oxidation state. It's an oxidation reaction. But it cannot happen by itself, because if there's oxidation, there has to be a reduction. So if this is to occur, there must be a reduction somewhere. If we write this reaction backwards, then it's the gain of electrons and it's a reduction. So this is going to occur with any of the ones below it written backwards. Lithium oxidation reaction will happen spontaneously with any of these down here written in the reverse. So what does that mean? So lithium likes to do this, likes to lose an electron. So if we pair lithium, say with with potassium, and we write potassium the other way. So here we're taking this oxidation, taking the oxidation and writing it backwards. So this is being reduced. It's gaining electrons. And these two half reactions will happen together because lithium likes to lose electrons and potassium ions like to gain electrons. She's shaking her head. Yeah, I've got a better one. Okay.
So we're taking metals, and we're essentially saying like, oh, if we put them together in a solution, this is what's happening.
Yeah, we're looking at if I put an ion of one metal and an atom of another, would the atom give electrons to the ion? And it will only go one direction. Let's see. How can I best illustrate? This goes back to the guys and girls at the party. So we had magnesium, right? And we put it in a solution of copper ions. So maybe that was copper 2 sulfate. And what happened was that the copper got the electrons, and then we've got magnesium sulfate. Really wasn't enough room there. So I put an anion in there to make it an actual chemical reaction, a molecular equation, not a net ionic equation. So this is how I think about this. Here's magnesium. Does he have a partner? No. Magnesium's going to the party all by himself. Does copper have a partner? Yeah. Copper and sulfate are going to the party together. So they go to the party. We're not going to have technically a precipitation reaction occur, But what's going to happen is that sulfate's going to decide that magnesium is a lot more fun to be with, and so she's going to leave copper, and copper's going to go home by himself. I know, it's brutal. Right? Does that make sense? Yeah, I'll get to the activity series in just a minute. So, from this encounter, we can say, well, magnesium is more desirable to the ladies than copper is, right? And so if this happened at another party, magnesium would go home with the girl. It's higher. So this is like a list of popularity or macho-ness or fineness or whatever the current word is. There used to be a Saturday Night Live skit and he talked about ¿Quién es muy más macho? So yeah, this is my list of muy más macho. So lithium is the machoist. He's the hottest guy, right? Lithium always gets the girl. He can take the girl from anybody else. Potassium's pretty hot too, but he can't take a girl from lithium. But potassium can take a girl from anybody up below him. Is that a little easier to think about? Yeah. So if I had magnesium and manganese, ooh, that wouldn't be confusing at all. So here, if I've got magnesium and manganese, is that reaction going to happen? So this is manganese with the girl, right? He's got a charge. He's charged because he's got the girl, right? And he's not charged because he doesn't have a girl. He's by himself, he's zero. So they come to the party, and who gets to leave with the girl? Whoever's higher on the list. Here's magnesium, and here's manganese. Magnesium gets the girl. So this reaction will happen. We'll end up with magnesium ion, and poor manganese goes home by himself. What if we had let's keep to our same pattern. What if we had silver and iron? Silver came by himself, and he's going to go home alone too. Because on this list, iron is higher on the list. Iron's more desirable. Iron gets the girl. Silver's down here. The one with the charge is the one that has the girl. He's charged up because I got this cute girl with me, right? So here, even though I'm not showing who the girl is, iron has her. And silver is not cool enough to take the girl from iron, and so nothing's going to happen here. Silver will remain alone, and iron will keep the girl, unless iron runs into somebody above him, like lithium, and lithium could take the girl from iron. Yeah.
Can we talk about the girls?
Can you talk about the girls?
Yeah, let's talk about what the girls actually like. So it wouldn't just be these two things. We're trying to see which one would.
So really, it's the electrons.
Yeah.
So the girl is really secondary to this. So it's the transfer of electrons. In order to become this ion, magnesium has to lose 2 electrons. And in order to go from an ion to an atom, it has to gain 2 electrons. And so it's about which metal is more likely to lose electrons, which is more likely to gain electrons. I find that hard to remember, though. And just thinking of this list, this is how I've always thought of it. It's my own little, strange chemistry world. And actually nothing is happening to the girls. The girls are unchanged. The anions are unchanged by this. It's just who they're with, right? And so that's why we can write a net ionic equation. It doesn't even have the girl in it. It doesn't matter what girl it is. And of course, just a disclaimer, none of these analogies are meant as inferences on actual people or places or anything, right? It's just something to help us figure this out. Any questions?
What is the Mg2 plus 2? I don't know that's saying just what you just said.
This one here?
Well, no, like all of the symbols seem to add with electrons. Like why are some 2 electrons?
Oh, why are some 2 electrons and some are 3 and some are 1? Because
The charges?
it's because of the charges that those ions form.
That's what that's saying. So it needs to be opposite.
Yeah. So when aluminum reacts, it's always going to lose 3 electrons because aluminum always forms a +3 ion. Now, something like chromium can form different ions, and so we're simplifying this a little bit, and we're leaving out the other chromium ions. Iron can form 2 different ions, but in here we're only looking at the iron 2 ion. That make sense? Why do they send this to me? Emergency alert. Attention MCC, Madera Center. There will be fire alarm elevator testing on campus this morning. Why do we need to know that? Can't they? Okay, let's look at this. Which metal is most easily oxidized? Yeah, question.
Why was mercury bolded?
Why was mercury bolded? Because it's hydrogen. This is actually not mercury. It's hydrogen. Yeah, it looks like mercury, and all the others are metals, and so we would kind of assume that is, but it's hydrogen. And it's bolded to point out that it's not a metal. It's hydrogen, and so that comes into play with which metals are going to react and dissolve in acids, and which will not.
I saw the G in the parentheses.
Yeah, the G is the gas, and yeah, it plays with our brains. Okay, so which metal is most easily oxidized? So how do we think about this? Well, what's oxidation? So loss of electrons or the increase in oxidation state, right? So if sodium becomes oxidized, it's going to become Na+, and to do that, it's going to have to lose an electron. So this is sodium without a girl, and this is sodium with a girl. So who is most easily oxidized of these 3? We're asking which of these is most likely to end up with the girl. So we look at the list, and we're looking for the one that's highest on the list, right? So we got sodium up there, lithium, potassium, calcium, sodium. So that's the first one. It's above chromium and gold. And so sodium is the most easily oxidized. It's highest on the list. Yeah.
Are we going to memorize the exam where
You do not need to memorize the activity series. So on an exam, you will either be given a list like this, or you will be given a partial list that includes the stuff you need. Yeah, I don't remember that list either, because that's actually not the whole list. There's a whole bunch of other stuff in there. Okay, determine whether each redox reaction is spontaneous. We can write a reaction, but it might not actually happen in real life. It might not actually go. So this is how I think about this. Here I have zinc with no charge and nickel with a charge. He's charged up because he's got a pretty girl on his arm, right? And so in this reaction, nickel loses the girl and zinc gets the girl. So for this to happen, zinc must be higher on the list than nickel. Does that make sense? For zinc to take the girl from nickel. And so then we have to go and look at the list. And we're looking for zinc and nickel. There's nickel. And here's zinc. So zinc's higher on the list. Zinc's more desirable to the women. So zinc is going to take the girl from nickel. So this one is spontaneous. Does that make sense? It'll happen, it'll go forward. Zinc and calcium. So here, calcium's got the charge. Calcium has the girl. If this reaction is to occur, zinc has to be able to take the girl from calcium, becoming the zinc ion, and leaving calcium out in the cold. So again, we have to go back to the chart, and we see that calcium is above zinc. Calcium's higher on the list, and so calcium's going to get the girl in the end. So here, calcium starts out with the girl, and he's going to keep the girl, and this reaction is not actually going to happen. Yeah, does it match with the chart or not? Does it happen or not? Spontaneous and non-spontaneous are just the terms that we use in the rest of chemistry. And what we'll find out is that you can make a non-spontaneous reaction occur, but it doesn't happen spontaneously. You have to force it to happen. So how might you convince this woman to leave with the guy that's not so fun? Make up a story. You're going to pay her money, or who knows? I don't know. Make up anything you want. But could that happen? It could, but it's not the normal way that things work. So this would not happen spontaneously. It would have to be driven by some outside energy source. That's why we use those words. Yeah?
Spontaneous is just another way of saying like naturally.
Naturally occurs. Yep. It's like, balls roll down the hill spontaneously. You don't have to do anything. They just do that spontaneously. Spontaneous means that, it doesn't need to get started, right? You don't have to push it or anything. It just happens.